You've probably been told your whole life that everything is made of tiny particles, little balls of matter bouncing around in empty space. And that picture feels intuitive, right? But physicists quietly abandoned that idea decades ago because it doesn't actually work. When you look closely at how an electron behaves, it doesn't act like a ball at all. So they had to rebuild the entire picture from scratch and discovered something underneath that has no surface, no edges, and no fixed location. What they found was that space isn't an empty container waiting to be filled. It's a physical medium, a property of space itself, and it's active even when nothing seems to be there. Picture yourself standing on a beach, watching waves roll in. Someone next to you asks what the wave is made of, and you say water, obviously. But think about that for a second, because the wave isn't actually a chunk of water you could scoop into a bucket and carry home. It's the water moving, doing something, and the wave only exists as long as that motion keeps going. That one simple idea, the difference between a thing and a thing doing something, is exactly what forced physicists to rebuild their entire picture of matter from the ground up. The picture most of us grew up with felt pretty solid, right? Atoms like tiny solar systems, a nucleus sitting in the middle, electrons orbiting around it like little planets, everything neat and countable. That model gave us chemistry. It explained the periodic table. You could draw it on a napkin, and it made sense in a way that felt satisfying, like the universe was just really small billiard balls clicking around each other. Then, physicists started measuring electrons more carefully, and the electron just refused to cooperate. It didn't sit in one place. When they ran experiments, it showed up in two places at the same time. It seemed to respond differently depending on whether anyone was measuring it, which shouldn't mean anything to a tiny ball, because a ball doesn't know it's being watched. No amount of tweaking the solar system model could explain any of that, so the model had to go. The answer that replaced it isn't smaller balls. It doesn't have a surface at all. Physicists realized the question, "Where is the electron?" was the wrong question entirely. Asking what the electron is doing to the space around it was the right one. What they found is that the electron isn't some small object sitting inside space the way a marble sits in a bowl. It's a disturbance in something that fills all of space, the same way a wave is a disturbance in the ocean. Every type of particle you've ever heard of has its own field like this, stretching across the entire universe. And these fields aren't built from something smaller or made of tinier pieces because they're the bottom layer, the thing that space actually is when you zoom all the way in. So when the electron field is quiet, undisturbed in some region, there's no electron there. When energy gets concentrated into it, when the field gets excited in a specific spot, a particle appears. Not because a particle showed up from somewhere else, but because the field itself is doing something local, a peak forming in the ocean, and just like a wave on a beach, it's the field doing the work, not some separate object traveling through it. That completely changes what you think you're touching. When you pick up a cup, the cup feels solid because the electron fields in your hand and the electron fields in the cup are pushing back against each other. The electromagnetic field between them gets disturbed, passing energy back and forth through virtual force carriers. And what you feel as solid matter is that exchange happening at close range. And even in the emptiest region you can find, a perfect vacuum with nothing in it at all, the fields are still there. They don't switch off. They just sit at their lowest possible energy. Quiet, but present. Everywhere. All the time. Poking one of those fields is where things get strange. And in the 1940s, physicists were trying to calculate exactly what happens when you do. The physicist who actually solved that problem didn't do it with bigger equations. He did it by drawing pictures. In the 1940s, physicists had a theory that described how electrons and photons interact, and it was the most accurate theory anyone had ever written down. The only problem was that every time someone tried to use it to calculate something concrete, the answer came back as infinity. Not a huge number, actual infinity. And a young physicist named Richard Feynman decided to fix that. To feel why that mattered, you need to understand how bad the problem actually was, and how crowded the field was with people trying to solve it. At a major physics conference in 1948, a physicist named Julian Schwinger spent an entire day working through his solution in front of the room, filling the board with dense algebra that most of the audience couldn't follow. It was exhausting to watch. Then Feynman got up and drew pictures. The theory, called quantum electrodynamics, worked beautifully in the abstract, but the method everyone used to pull numbers out of it involved expanding the math into a long series of terms and adding them up, kind of like an infinite checklist of contributions, where each term on the list was supposed to be smaller than the last. The first term gave a sensible answer. The second term blew up into infinity, and the more carefully you tried to calculate, the worse it got. Physics was genuinely stuck. Feynman looked at that series of terms differently. He noticed that each term wasn't just a chunk of math sitting there, disconnected from everything else. Each one corresponded to a real physical process you could actually draw. An electron moving from one place to another, a photon getting emitted, two particles exchanging energy. So he built a visual notation for it, where lines stand for particles and the points where lines meet stand for interactions. And every single diagram maps directly onto one of those mathematical terms. A straight line moving forward through time is an electron. A wavy line is a photon. Where they meet is the moment of interaction. Each line and each meeting point is a literal instruction, a Feynman rule, telling you exactly what calculation to run for the probability of that event occurring, and you multiply those rules together to get a number. The diagrams didn't make the physics easier. What they did was organize it so you could actually work with it, instead of staring at one enormous equation that collapsed into nonsense. You could draw out every possible way a given interaction could happen, calculate the contribution from each diagram, and add them all up. The more diagrams you included, the more accurate your final answer got, and the answers started coming out right. How right? The prediction for a specific magnetic property of the electron, a value measured at 1.001147, agrees with what you actually measure in a lab to better than 1 part in a billion. No other method in any field of science has ever come close to that kind of accuracy. And crucially, the diagrams gave physicists a way to finally deal with those infinities. By carefully tracking every diagram and redefining what you mean by the mass and charge of an electron, you could absorb the infinite terms and extract finite, meaningful predictions. That process, called renormalization, is what broke the 20-year logjam and turned quantum electrodynamics into a working tool. What that tool revealed about forces is where the picture gets genuinely strange. Everything you've been told about forces, that there are pushes and pulls, that one magnet shoves another across empty space, that gravity just reaches out and grabs you. That whole picture breaks down at the quantum level. Not slightly, completely. And the real answer makes a lot more sense once you see it. In the field picture, two electrons can't just feel each other across a room with nothing happening in between. Something has to carry the information from one to the other, and that something is an excitation in the electromagnetic field sitting between them. When two electrons get close and repel each other, what's actually happening is that the electromagnetic field between them gets disturbed, and that disturbance carries energy and momentum from one electron to the other. Physicists call this a virtual photon. Not because it's imaginary, but because it only exists as part of the interaction itself, and you can never pull it out and measure it directly. It's the field doing the work of what we used to call a force. This idea was actually worked out before quantum electrodynamics was fully built. A physicist in the 1930s reasoned that if every force gets carried by a field excitation, then the range of that force depends on the mass of the particle doing the carrying. A massless carrier, like the photon, produces a force that reaches across infinite distance, which is exactly what electromagnetism does. A massive carrier can only travel a short distance before its energy runs out, so it produces a short-range force. When physicists explored the nuclear force, the one that holds protons and neutrons together inside an atomic nucleus, they predicted a carrier particle with mass called the meson, and the range of the nuclear force matched that prediction exactly. So the force isn't a separate thing layered on top of the particles. The field is the force, passing disturbances back and forth between excitations. There's no invisible rope connecting two electrons. The field is the rope, and it's made of the same stuff as the electrons themselves. Now, when you try to calculate exactly how strong these interactions are using Feynman diagrams, you run into the infinities again. Some diagrams include loops, where a virtual particle travels in a closed circle and feeds back into the interaction. And those loop diagrams don't just give large numbers. They give infinity. And it's not a mistake in the calculation. It's sitting right there in the structure of the theory. Physicists eventually worked out what those infinities were actually saying. The theory uses specific values for things like the mass and charge of an electron. But when you include all the loop diagrams, those values get contributions from processes at every possible energy scale, including arbitrarily high ones. And that sum blows up. The fix, called renormalization, treats the bare values in the equations as placeholders and redefines them so that what you're working with are the actual measured values from experiment. The infinities get absorbed into those redefinitions, and what's left are finite, usable predictions. Feynman himself called it a shell game because it felt like you were hiding the problem rather than solving it. But the predictions matched experiments with extraordinary accuracy, and over time, physicists realized renormalization wasn't a trick. It was a statement about how physics actually works at different scales, a way of cleanly separating what happens at low energies from what happens at high ones, so the theory stays useful. The infinities were the theory flagging its own boundaries, and that realization opened the door to something much bigger. A single framework that could organize every particle and every force physicists had ever found. That framework is called the Standard Model, and it fits on one page. By the 1970s, particle accelerators had been churning out new particles for decades, and the list kept growing faster than anyone could make sense of it. Physicists weren't just confused. They were drowning in data, with no clear picture of why any of these particles existed or how they connected to each other. Then, over a period of years, that chaos got organized into a single framework, and it fit on one page. The Standard Model takes quantum field theory and applies it to 3 of the 4 forces we know about: electromagnetism, the weak nuclear force that drives radioactive decay, and the strong nuclear force that holds atomic nuclei together. Each force gets its own field and its own carrier particle, but they're all written in the same mathematical language, and that language is built around symmetry. Those symmetries aren't decorative. They're the reason the forces exist at all, because every force in the Standard Model drops out as a direct consequence of a symmetry the theory has to respect. And because of a result called Noether's theorem, every symmetry produces a conservation law. The symmetry of electromagnetism is exactly why charge is always conserved. Take the symmetry away, and the force disappears with it. That worked beautifully until physicists looked at the particles that carry the weak force, called the W and Z bosons. According to the symmetry rules, they should have been massless, like photons, because the symmetry didn't allow them to have mass. But they're not. They're among the heaviest particles ever detected, and physicists struggled to explain the weight of these particles because a massless carrier and a massive one behave completely differently. The mystery led researchers to a new field sitting on top of everything else, filling all of space, now called the Higgs field. Particles that would otherwise be massless according to the symmetry rules don't travel freely through it. The Higgs field resists their motion, and that resistance is what mass actually is at the quantum level. Different particles couple to the Higgs field with different strengths, so they pick up different amounts of mass. An electron barely notices it. A top quark couples so strongly that it ends up nearly 200 times heavier than a proton, and the W and Z bosons couple to it just enough to get the masses we actually measure in experiments. The Higgs field also produces its own excitation, the Higgs boson, and physicists predicted its existence in the 1960s. Confirming it took until 2012, when the Large Hadron Collider at CERN finally produced one. To get there, physicists smashed protons together at close to the speed of light, billions of collisions per second, sifting through the wreckage for a signal that showed up roughly once in every 10 billion events. When it appeared, it matched the prediction almost exactly. That confirmed the last missing piece. The Standard Model now had experimental support for every particle it predicted. And yet it has no quantum description of gravity at all, says nothing useful about dark matter, which accounts for most of the matter in the universe, but doesn't interact with any Standard Model field, and can't explain why matter won out over antimatter after the Big Bang. A proposed collider called the FCC, 4 times larger than the LHC and the physics community's highest priority for finding answers to dark matter and the matter-antimatter problem, is being planned specifically to find where those predictions start to crack. The Standard Model describes every particle ever detected in an accelerator with extraordinary accuracy, and it still can't account for roughly 95% of what the universe actually contains. Which means the fields are still out there, doing something we haven't figured out yet. What that framework actually says is that the vacuum of space isn't empty. It's every quantum field sitting at its lowest energy, humming across all of space. And the only reason anything exists is that those fields can be pushed out of that quiet state and concentrate into a stable ripple we call a particle. You aren't a collection of tiny balls. You're a knot of field excitations that's been stable long enough to read a YouTube video about it. That same framework now drives real technology. Labs are suspending neutral atom qubits in laser beams and running algorithms that could crack RSA encryption within years, not decades. And yet the fields we've mapped so far only account for about 5% of what the universe actually contains. Every particle ever detected in an accelerator fits neatly into the Standard Model, and that still leaves dark matter, dark energy, and the matter-antimatter imbalance completely unexplained. The fields we know aren't the whole story. They're just the part we've managed to see.